go ahead. Okay, so Alessandro,
are you able to see my screen? Is it okay?
Yes.
Okay, fine. So thank you everybody for this nice conference and for giving me the opportunity to participate with this small contribution. So I'm Alessandro LOPPINI from Campus Bio-Medico University of Rome, and in this talk I will discuss about temperature-dependent response and correlation properties of cardiac tissue. So cardiac dynamics present complex spatiotemporal phenomena, and among these we can find normal rhythm and regular activation maps, and rhythm regimes and irregular activations, which are typically linked to fibrillation and spiral waves. And sometimes in cardiac transition from normal rhythm to tachycardia and fibrillation, cardiac alternance can also be observed, which are periodic bit-to-bit variation of action potential duration and diastolic interval. Cardiac alternance can be investigated by the use of restitution curves by taking into account several parameters such as the action potential duration, the diastolic interval, but also the conduction velocity. So additional complexity comes into play if we consider also the feedback from other physical quantities, such as the temperature. Indeed, it has been proven that the temperature may alter excitability, the conduction velocity, and also the action potential duration, and sometimes also action potential amplitude, with significant effects on the emergent activity and dynamics. This was historically shown on neuronal dynamics and was further proven to be valid also on cardiac response. As you can see on the slide, experimental results on rabbit and squirrel shows grid variation with respect to temperature, considering the activation maps in our tissue. A deep understanding of this complex dynamics requires the use of extensive mathematical modeling, which can be used in combination with experiments. So with these premises, in this slide I present both some experimental data and a mathematical model which is fine-tuned on experiments to reproduce temperature-dependent modulation on cardiac emergent dynamics. Concerning the experiments, were performed by Professor Fenton and Professor Gizzi in Cornell on canine ventricles treated with a specific voltage-sensitive dye and with blebbistatin, which is used to overcome muscle contraction and motion artifacts. Both endocardium and epicardium were optically mapped during different pacing down restitution protocols, realized by stimulating the tissue with a fixed electrode on the endocardium surface, starting from high pacing cycles and progressively reducing the stimulation period. In this slide, you can see some representative recording extracted from 2 points on the endocardium surface, showing transition from normal rhythm up to cycle 2 alternance. So in this case, the action potential duration repeat every 2 cycles, up to ventricular fibrillation. And there is also shown a small range with ventricular tachycardia. And in some cases, also higher order alternance can be observed in the transition between normal rhythm and fibrillation. Higher order alternance in the sense that actually the action potential duration can repeat every 4 cycles or every 8 cycles in a cascade of period doubling bifurcation before arriving at the fibrillation onset. Concerning the mathematical modeling we used to reproduce this kind of experimental behavior, we adopt a phenomenological model known as minimal model, which takes into account the dynamics of 4 variables, which are the non-dimensional membrane potential and 3 gating variables regulating the activation and inactivation of ion currents. In particular, the ion currents included in the model are fast inward sodium, slow outward potassium, and a slow inward calcium current. Temperature feedback is further introduced by using Arrhenius and Moore factor, which actually are introduced to model the feedback of temperature on the activation time constant and inactivation time constants and on the maximal conductance variation. All the modeled parameters concerning also the parameter regulating the Arrhenius and Moore factor are fine-tuned to reproduce experimental data. So carefully fine-tuned to reproduce both action potential shape and restitution curves as observed in experiments. In this slide, you can see some simulation results performed on a one-dimensional cable, in this case to show the action potential shape. A particular point on the domain is extracted. You can see that at low temperatures, the action potential duration is much more greater compared to the action potential duration at lower temperature. And also the conduction velocity is significantly affected by temperature. So it significantly increases at high temperature and decreases at low temperatures up to 26 degrees Celsius. And this behavior is recovered both for endocardium and for epicardium, and this is consistent with experimental data. We also evaluated the model performance by computing restitution curves in every thermal bath analyzed. And in this case, these restitution curves are computed along two consecutive beats during the restitution protocols. And as you can see, can you see my video?
No.
Sorry.
We see the slide.
I was able for a while to see your video.
Sorry for that. Let's try to start again. Do you see my video?
No, we don't.
Can I pause the sharing for 1 second just to fix the video?
Otherwise, never mind. Please go ahead.
Let me try to restart again.
Wrote that able to see the video.
Can you see the
like
video now?
someone can see the video. Maybe not everyone. I'm not.
Let me try to restart again.
Able to see you.
Okay, let me try to restart the presentation.
Okay, thank you.
Is it okay now?
Yeah, perfect.
Okay, sorry for the problem. So in this case, we computed these restitution curves over all the temperatures analyzed. As you can see, at higher temperatures, the action potential duration significantly decrease. But what is also interesting from these restitution curves is that if you analyze the slope equal to 1 of this curve, which is usually linked to the transition point between normal rhythm and alternance, this critical point is shift to higher cycle lengths at lower temperature, indicating a higher risk of alternance and fibrillation in hypothermal condition. And this behavior is recovered both for endocardium and epicardium and is consistent with experimental data. To further analyze this transition of the critical point on which is observed this transition in alternance, we further performed a simulation on a one-dimensional ring. In this case, a standing wave is opportunely initialized on one ring. So once the standing wave is stimulated on the tissue, the length of the ring is sequentially reduced to simulate an increasing cycle length, despite the standing wave is always the same. In this kind of analysis, we didn't average between the action potential diastolic interval over the 2 beats, but we consider every beat in the stimulation protocol. So it is possible to observe the splitting of the restitution curve in response to the reduction of the length of the ring, which is equal to the reduction of the cycle length actually. And we can see that the splitting of the curve and the alternance onset is shifted on the right for lower temperature, which indicates a higher risk of alternance. I mean, the alternance is triggered at higher cycle lengths at lower temperature, so in hypothermal condition. So this hypothermal condition are linked to an increased risk to develop alternance and fibrillating regimes. What is also to be noted is that alternance onset does not correspond to the same circuit length between endocardium and epicardium, and this indicates a non-synchronous behavior between the two surfaces. Also, the progressive reduction of temperature gives rise to more enhanced alternance, represented by a higher bifurcation amplitude at lower temperatures. So, now that we address the complexity of the cardiac dynamics, how can we characterize cardiac dynamic regime and its transition? So the transition between normal rhythm and fibrillation, alternance and then fibrillation. So we refer to the literature to find out what are the most promising indicators to identify this dynamic regime and the transition between cardiac regimes. And we found out that several studies used the concept of correlation length to analyze the fibrillation. So we try to generalize this concept of correlation length to investigate also the normal rhythm in the heart and also the alternance regime. So in this case, we also rely on both mathematical modeling and experiments to perform this kind of correlation analysis and analyze what are the correlation length recorded in normal rhythm, in alternance, and also in fibrillating regime. Concerning the model, in this case, the simulation were performed on two-dimensional domain, trying to simulate the actual shape of the tissue. In this case, the actual shape of the tissue is taken into account in the model via phase field approach. And most of all is also introduced a certain degree of anisotropy and heterogeneity by introducing an adoptive diffusion tensor, where the anisotropy ratio is 3:1. So along the direction of the fiber, the diffusion coefficient is 3 times the ones on the respect to the transversal direction. And heterogeneity comes into play by considering the local direction of the fibers. So both anisotropy and heterogeneity are considered here to find out, to reproduce in a correct way the activation maps respect to experiment. In this slide, you can see experiments result compared to the modeling in a particular reference case. As you can see, the model can match the experimental activation map in terms of conduction velocity, in terms also of wavefront shape, and also other features, all the other features of the emergent activity. So with these premises, both on the experimental maps and on the simulated maps, we performed a spatiotemporal correlation analysis. In this case, for each frequency along the restitution protocols, we investigated a square box within the mapped field and the simulated field. And within this box, we computed a 2-point correlation function, taking into account every point in the domain. So in every calculation within the box, we select each point within the box and evaluate its correlation with all the other points within the domain. We perform this kind of computation for all the for the points contained in the box. And finally, all the correlation indices are averaged within the box to obtain a unique correlation function dependent on distance. In this case, the bracket operator you can see in the definition of the 2-point correlation function stands for a time average. In this case, the time windows we selected to perform this kind of computation is consistent with 1-bit cycle. And we perform this kind of computation for every 2 bits, 2 consecutive bits in all the restitution protocols. Based on this correlation function dependent on distance, and by hypothesizing an exponential decay of this function, we identified the characteristic length as the L0 in this exponential expression, and evaluated this L0 for all the 2 bits for every pacing cycles within the restitution protocols. Of course, the L0 is estimated by a linear fitting on the semi-log plot of the correlation function plot. Concerning the results, it is shown that the characteristic length are regular regimes, so in normal rhythms, and at fairly high pacing cycle is fairly high, is almost equal to 40 centimeters, but there is a drop in the correlation length at decreasing pacing cycle. And up to the case of alternance onset, where the characteristic length falls down up to 10 centimeters and up to 2 centimeters close to the fibrillation onset point. In this case, the plot relates to 9 different experiments performed, analyzed. And while the solid line with black circle concerned with the modeling result, which are in agreement with experiments. So also for the models, the characteristic length computed with this procedure is consistent with the one observed in with experimental settings. To analyze the interbit variation, I mean, in this case, sorry, I skipped a point. In this case, we average between the two consecutive bits, the two characteristic lengths computed, but we want also to analyze the interbit variation of the characteristic length. So in a second analysis, we perform an ad hoc normalization of the characteristic length. So basically, we studied the averaged characteristic length among two consecutive bits and use this average value to normalize one of the two lengths. As it is defined by taking into account the first of the second length is totally invariant because the measure is symmetric. But what is interesting in analyzing this normalized length is that at low pacing cycle, at least for the experimental part, this interbit variation of the characteristic length is different from zero. So there is some interbit variation of the characteristic length, which is not recovered by the model. And this interbit variation at very high pacing cycle is due to tissue intrinsic dispersion. When the pacing cycle is further reduced, there is some point at which the characteristic lengths fall to zero, and this is consistent with a synchronous response of the tissue. And after that, at high pacing cycles, so very high, very low pacing cycles, so very high pacing frequency, there are some kind of oscillations of the characteristic length which are linked to the alternance onset. So the power of this indicator is that when the alternance is on play, there are strong oscillations of this normalized length, which is a measure of interbit variation of the characteristic length. It is I mean, notably, this kind of behavior is not recovered by the model. I mean, the different value at high pacing cycle of the characteristic length different from zero is not recovered because the model cannot reproduce the intrinsic tissue dispersion, and also the oscillations are not recovered by the model. And this can be done to some misleading ingredients, to some ingredients which are not included in the model, such as the memory effect and probably some other detailed mechanism, biophysical mechanism. So what about fibrillation? We see that there is a drop in the characteristic length along all the restitution protocols. Usually the characteristic length is about 2 centimeters in alternating regime. In what we found in fibrillation, both in experiment and in modeling results, is that the characteristic length falls to about 1 centimeter. And this is in agreement with previously reported results on the correlation length computed on other kind of experiments. And this makes us confident on the validity of the computed results on the normal rhythm and also on the alternance regime. So to conclude, cardiac dynamics is characterized by complex spatiotemporal behaviors, which is further enriched by feedback from other physical quantities, such as the temperature. This complexity can be reproduced by fine-tuned mathematical models, and simulation can be of help to understand the underlying mechanism regulating these complex dynamics, and also the variation of the emergent dynamics respect to temperature changes. And also characteristic length represents a useful indicator to describe the cardiac dynamical regime, and also, and most of all, the cardiac transition, I mean, cardiac transition between cardiac dynamical regimes. And in the future, thermoelectric cardiac models can be used in combination with correlation analysis to investigate the thermal effects on the characteristic lengths and also on cardiac transition. We are currently working on this point, and we are confident we will be able to submit this work in the next months. So I stop here. I thank you for your attention. I thank also all the people that contributed to this work and the people coming from the lab. So Alessio Gizzi, Cristian Cherubini, Elisabeth Cerri, Flavio Fenton, and Simonetta Filippi. So thank you, and all the questions are welcome.
So thank you, Alessandro. I think we have a very short time for maybe 1 or 2 quick questions. If there is any, please raise your hand or just write a message in the chat.
I will stop the sharing, sorry. Okay, here I am. Sorry for the problem with the video, I was not aware of this.
So if nobody has questions, actually, oh, sorry, so I'm checking. Okay, so nobody, no participant raised his hand. So I actually have a curiosity. Have you ever thought about extending your models to three-dimensional geometries? Do you think it can be more useful for
Yeah, I mean,
people?
it is for sure interesting. I mean, it is not straightforward to investigate all the restitution protocols in 3D settings because the simulation are very demanding. So it can be done in principle, but it is really challenging because you have to simulate the tissue for all the pacing down protocols, and it can be really challenging. So I think you need a big cluster and also several computing time, but it can be principle done. We are working on this, and probably in future works it will be much more feasible. But yes, we think about that. I mean, also in two-dimensional simulation is already challenging.
I'm sure about it.
Yeah, but thank you for the question. It will be interesting for sure to investigate this point.
Okay, so if nobody has other questions, I think we can thank Alessandro again.